Imagine a world where your memory, learning speed, and mental clarity are not limited by biology alone. By 2025, biointegrated cognitive augmentation devices are set to transform how we think, learn, and interact with information. These devices, now entering first-in-human trials, promise to seamlessly blend biological and electronic systems, directly interfacing with our neural tissue. This isn't science fiction, it's the next leap in human evolution, driven by the need to keep pace with the overwhelming data and demands of modern life. Today, we embark on a journey to explore how these innovations will reshape our brains and our society. Every day, humanity generates 2.5 quintillion bytes of data, an amount our brains, evolved for survival rather than information overload, simply cannot process efficiently. The gap between the speed of our biological neurons and the power of silicon processors is widening. This growing disparity motivates scientists and engineers to develop biointegrated electronics that can enhance our cognitive abilities from within. The goal is to empower our minds to keep up with the digital age, making sense of vast information streams and unlocking new levels of mental performance. Three main types of biointegrated devices are leading this revolution: ECOG-derived mesh nodes, microled optrodes, and synaptic scatterlets. Each is designed to interact with the brain in unique ways, offering new possibilities for recording, stimulating, and even mimicking neural activity. These devices are ultra-thin, flexible, and capable of operating without batteries or wires, making them minimally invasive and highly adaptable for long-term use. Let's dive into what makes each device special and how they work together to enhance cognition. ECOG-derived mesh nodes are ultra-thin, flexible polymers that conform perfectly to the brain's surface. They record and stimulate neurons with remarkable precision, down to 0.8 millimeters, which is 10 times finer than traditional pacemaker electrodes. These mesh nodes feature bioresorbable coatings, operate at sub-zero 5V, and transmit data ultrasonically. Their design ensures minimal invasiveness and allows them to dissolve safely after their job is done, reducing the need for surgical removal. Microled optrodes are as thin as a strand of hair, combining electrodes and tiny light emitters. These devices enable optogenetic control of neurons, meaning they can activate specific brain cells with light, all without the need for bulky fiber optic cables. With millisecond precision, optrodes can stimulate neural circuits in real time, opening new doors for targeted therapies and rapid cognitive enhancement. Their wireless, battery-free operation makes them ideal for long-term brain integration. Synaptic scatterlets are tiny, just 50 micrometers across, and work passively by harvesting energy from the body's own arterial pulses. These battery-free grains can release neurotransmitter analogs on demand, mimicking short-term memory processes. Their ability to operate without wires or batteries and to dissolve safely after use makes them a promising tool for temporary cognitive boosts and targeted brain therapies. A key feature of all these devices is their wireless, battery-free operation. They communicate using ultrasonic backscatter, allowing data to be transmitted safely through brain tissue. Their bioresorbable materials mean that after their work is done, they dissolve naturally, minimizing the risk of long-term complications or the need for additional surgeries. This approach is a major leap forward in making brain augmentation safe and accessible. These devices bridge the gap between the brain's ionic signals and electronic data. For example, mesh nodes detect tiny changes in potassium ion concentrations. Just 30 millivolts digitize the signal at 20,000 times per second and send it ultrasonically to a relay device. In reverse, a 40 kHz ultrasonic ping can power micro-LEDs, triggering neuron firing with a latency of just 6 milliseconds, faster than the blink of an eye. This seamless communication is the foundation for real-time cognitive enhancement. Early clinical trials are already showing promising results. At EPFL in January 2025, mesh nodes restored 19% of working memory in patients with mild cognitive impairment. This effect was statistically significant and sustained for 8 weeks, with no adverse effects like microhemorrhages or abnormal tissue responses. These findings suggest that biointegrated devices could offer real hope for those facing memory loss and cognitive decline. At UCSF, optrodes led to a 32% improvement in verbal memory encoding, effectively reversing 23 years of cognitive aging during stimulation. While safety data is still being gathered, these results highlight the transformative potential of targeted brain stimulation. Such advancements could soon help millions regain lost cognitive abilities or even surpass their previous mental performance. The software layer is just as revolutionary as the hardware. Transformer-based AI decoders are trained on each user's unique neural patterns, predicting the brain states that precede correct answers. The AI then nudges neural circuits toward these optimal states, acting like an autocomplete for your mind. This real-time guidance can boost learning, memory, and problem-solving, making the brain more efficient and adaptable. With such powerful technology, privacy and ethics are paramount. All neural data is protected by 128-bit on-device encryption, with a 2-second rolling buffer and opt-in cloud syncing. Streaming or external access to thoughts is strictly prohibited. These safeguards are designed to protect user identity and autonomy, ensuring that cognitive augmentation remains a tool for empowerment, not exploitation. In the near future, these devices will accelerate stroke rehabilitation by more than double, helping patients remap their brains and regain lost functions. For PTSD, real-time modulation of the amygdala can dampen hyperactive responses, offering new hope for trauma survivors. These applications demonstrate the immediate, life-changing impact of cognitive augmentation in clinical settings. High-stakes professions like military, air traffic control, and surgery require years of training. With biointegrated devices, the time to mastery could shrink from 10,000 hours to just 1,500. In education, these tools can support students with dyslexia or ADHD, providing cognitive boosts without the need for medication. This technology promises to level the playing field and unlock human potential on a massive scale. Despite their promise, these devices face significant risks. The body's immune response can cause fibrotic encapsulation, degrading signal quality after about 18 months. Overstimulation from optogenetic devices may lead to excited-excicity, damaging neurons. Closed-loop AI systems could unintentionally reinforce cognitive biases or suppress creativity. Addressing these challenges is crucial for safe, effective brain augmentation. Regulatory agencies like the FDA and EMA require extensive safety data, up to 6 years of follow-up and ongoing surveillance for complications like intracranial bleeding. Cost is another major hurdle. Current implants cost around $48,000, but widespread adoption will require reducing this to about $3,000. Overcoming these barriers is essential for making cognitive augmentation accessible to all. The next 5 years will see rapid progress. By 2026, multi-center trials will target memory, attention, and mood. In 2027, fully bioresorbable devices will dissolve after 24 months, eliminating the need for removal surgery. By 2028, the first memory prosthesis for Alzheimer's disease could receive accelerated approval. Consumer-grade, non-surgical neuromodulation pods are expected by 2029, and by 2030, a global summit may propose a cognitive liberty amendment to the UN Declaration of Human Rights. A live demonstration showcased the power of these devices. A user solved a Rubik's Cube blindfolded in just 47 seconds, guided by real-time neural decoding cues delivered via bone-conducted pulses. For comparison, the average novice takes 8 minutes. This feat illustrates how biointegrated technology can dramatically accelerate learning and problem-solving, making the extraordinary achievable. As mind-machine integration becomes a reality, the concept of cognitive liberty takes center stage. This principle asserts that individuals must retain control over their own thoughts, memories, and mental enhancements. Safeguarding cognitive liberty will be essential as these technologies become more widespread, ensuring that augmentation empowers rather than controls. Societal implications of biointegrated cognitive devices are profound. They promise to blur the boundaries between what we know and what we can instantly access, potentially redefining education, work, and even personal identity. However, these advances also raise critical questions about equity, creativity, and the preservation of individuality in a world where minds can be augmented. Proactive policy and ethical frameworks will be essential to guide this transformation responsibly. Biointegrated cognitive augmentation devices are not about turning us into cyborgs overnight. Instead, they represent a careful, science-driven evolution of what it means to be human in the digital age. As we move forward, the key challenge will be to harness these technologies for the benefit of all, safeguarding identity, equity, and creativity, while unlocking new realms of possibility for the human mind.